Well, what we learned yesterday, we start talking about confidence interval. Recall that to form the confidence interval for proportion, so if the question says, hey, construct the confidence interval for proportion of population, we need the following information. First, we need to find p hat, which is your sample proportion, Then we need our standard error, or which is denoted by sigma sub p hat, which we learned it's equal to square root of p times 1 minus p divided by n. Then we use p and n, we can construct the standard error. Well, after constructing the standard error, we need to find the margin of error. The margin of error denoted by E. The margin of error for 95% confidence interval is 1.96 times standard error, or sigma sub p hat, or square root of p times 1 minus p divided by n. So margin of error is equal to 1.96 times sigma sub p hat. After finding all of this information, we can say that, hey, the confidence interval for 95% confidence is p hat minus margin of error, comma p hat plus margin of error. So if you see a question and question says, hey, construct confidence interval for population proportion, you're going to follow these steps. The very first step is to find the sample proportion. The second step is to find the standard error, sigma sub p hat, which is equal to square root of p times 1 minus p divided by n. And finally, you need to find the margin of error E, which is 1.96 times sigma sub p hat. Sigma sub p hat is this number here. So after calculating this number, we just substitute that here, multiply by 1.96, and then our final step is the confidence interval itself. For 95% confidence interval, it is parenthesis p hat minus the margin of error, comma p hat plus the margin of error, and then we close the parenthesis. Well, okay, so before constructing the confidence interval for proportion, we need to check normality. The criteria to approximate normality. We can check the values of n times p and n times 1 minus p to approximate normality. So what is n? N is sample size or population size. In general, n is size. And p in this case, note that p doesn't have a hat on top of it. So it's not related to sample. It is just population. P is population proportion. So we're going to check normality. We need to find n times p. And also we need n times 1 minus p. After finding these two numbers, if these two numbers are larger than or equals to 10, we say that, hey, the normality is met. So calculate NP, calculate n times 1 minus p, when these two numbers are both larger than or equals to 10, you say that, hey, the criteria for normality is met, and you can officially start constructing the confidence interval for your proportion. Okay. Question 5 says, let us use the normal distribution to describe the sampling distribution of sample proportions. We're going to use what we had for M and M's. Remember that the size is 50. We're going to check the normality criteria. Well, okay, from previous page, we know that P is equal to 0.24 or 24%. The proportion in previous page was given to us as 0.24. What is N? Sample size is given to us as 50. So N is 50. Since the question says, hey, check the normality, it means that we need to find NP and also N times 1 minus P. Okay, to check normality, find NP and N times 1 minus P with these two. N is 50. I already have N, this size. P is given to me as 24% or 0.24. N is 50. Now 1 minus P, 1 minus 24%. When we do the calculation, when we multiply these two numbers, both of them are larger than, equals to 10. We can use our calculator to do the exact calculation to find these two numbers, and then we can see both of these two numbers are larger than or equals to 10. So it means that the normality is met. Well, now the normality is met. It means that I'm allowed to use these formulas to form the confidence interval. Let's take a look at part B and part C. Part B says, okay, the empirical rule tells us that about 95% of a normal distribution is within 2 standard deviations or 2 standard errors from the mean. Question says, use the mean and standard error from the blue M&M's example to give the interval which contains approximately 95% of sample proportions. We can also take a look at the dot plot, the graph here, and based on that, we can use the approximation. Note that P is given to us as 0.24, which is the same as before. The sample size that we can use is 50. Here you have 1,000 sample proportions. So it's taken 1,000 times from from M&M's bags, and we were looking for the blue colors. Okay, so we know the steps. The normality check. Normality is checked. The next one, we need to find P hat. Okay, so you might say, hey, since I don't have P hat, what should I do here? The only thing is given to me is P equals to 0.24. So in this case, instead of using P hat, we're going to use just 0.24. So 0.24. Next step, we need to find the standard error, sigma sub P hat, which is equal to square root of P, 1 minus P divided by N, which is equal to square root of P is 0.24, parentheses, 1 minus 0.24 divided by N, which is 50. Okay, now we need to use the calculation to find this number. Let us use our calculator. Let's turn on the calculator. Here we go. So I want you to calculate the square root of, so second x squared, and I have 0.24, so I'm going to use parentheses, times 1 minus 0.24. I'm going to close the parenthesis, and then I'm going to divide this by 50. So let's put everything in parentheses. So make sure everything is inside the radical, and it gives me, hey, 0.06, approximately 0.06. So my standard error approximately is 0.06. After finding the standard error, since I wanted to find the 95% confidence interval, my margin of error is equal to 1.96 times the standard error, which is 0.06. So multiply 1.96 by 0.06. Approximately, it gives me 0.18. 0.18. I have all the information that I need. So the confidence interval is equal to P hat 20.24 or 24% minus the margin of error 0.18, comma 0.24 plus the margin of error 0.18. So the confidence interval is approximately, here we have 0.6 0.6, and here I have 0.42. We can take a look at our graph here, 6% to 42%. It's almost here. 6% to 42%. Say that, hey, we are 95% confident that we are 95% confident that the population proportion is between 6% and 42%. So between 6% to 42%. As you can see, empirical rule says, hey, 95% of the population is within 2 standard deviations or 2 standard error. And by doing the calculation, this is the calculation that we did. We checked the normality, we found the sample proportion, standard error, margin of error, and we constructed the confidence interval, which is 6% to 42%. Our next step is to use the actual sample proportion to construct a confidence interval. Very well. In our next stage, we have more examples. Well, okay, it says, next steps, refining the empirical rule. If we use a normal curve to model the sampling distribution of sample proportions, we see a curve of similar center, shape, and spread to the dot plot above. The empirical rule tells us that approximately 95% of the values are within 2 standard errors or 2 standard deviations from the mean. If we wish to be more accurate, we can use the normal model to determine a more precise interval which contains 95% of sample proportions. So as you can see, instead of just using mu, we're using mu times mu sub p hat. And here we are multiplying 1.96 by standard error. This is now your standard deviation, mu minus mu plus. The normal model tells us that 95% of sample proportions are within 1.96 standard errors of the mean. This is similar to what we predicted by empirical rule, but it is more exact. So what do we need to know? When the criteria for normality are satisfied, remember that criteria for normality, NP is larger than or equals to 10, n times 1 minus p larger than equals to 10, the normal model follows this rule. The interpretation is 95% of all sample proportions are within 1.96 standard errors of the population proportion. Well, as a result of this fact, 95% of sample proportions have a deviation or error of less than 1.96 standard errors. We call 1.96 standard errors the margin of error. So our margin of error, as we calculated before, is 1.96 times the standard error, or represent this E, margin of error equals to 1.96 in mathematical terminology times sigma sub p hat. Remember that sigma sub p hat is square root of p times 1 minus p divided by n. In our next page, we're going to actually use this formula one more time and calculate the confidence interval. Very well. So now we are working with the case that P, or population standard deviation, is missing. It's not given to us. P is population standard deviation. Okay, we estimate the population proportion, or P, because we don't know its value. Remember that comes to population, it's very hard to gather information, enough information to calculate the population parameter. One of the parameters for population is proportion. So we have to estimate that. How do we estimate that? We use sample proportion p hat to estimate population proportion p. So from a small sample, we find p hat, and then we try to estimate the population proportion p. Okay, after estimating the population proportion using a sample proportion, we can find the estimated standard error. Remember that there is always a difference between p hat and p. We always make an error. How do we calculate that error? To estimate that error, we need to follow the formula square root of p hat times 1 minus p hat divided by n. Well, if the question says construct 95% confidence interval, the margin of error E is equal to 1.96 related to 95% confidence interval times square root of p hat 1 minus p hat divided by n, which is our standard error. You can use mathematical terminology to rewrite this as 1.96 times sigma sub p hat. After that, the confidence interval is super easy. Confidence interval is p hat minus margin of error, comma, p hat plus margin of error. So when you're constructing the confidence interval, this is your final step. If the final step is missing, it means that as a statistician, you couldn't come up with the confidence interval for 95% confidence. So make sure you have your final step written as the confidence interval. Parentheses, p hat minus e, comma, p hat plus e. Okay, give us an example. In the context of a confidence interval for an unknown population proportion, again, assume p is missing. P is not given to us, which is usually the case. We don't have the information, all information about population. So it's very hard to construct the population parameter. The criteria for approximate normality are satisfied if you have a random sample, which includes at least 10 successes and 10 failures. What's the meaning of that? How do we write this in mathematical form? It means that n times p hat is larger than equals to 10, and n times 1 minus p hat is also larger than or equals to 10. So in this case, we say that the criteria for normality is met. Now that we have the criteria for normality, we can find the estimated standard error, the margin of error, and the confidence interval. This is our ultimate goal. Try this. Okay. In the previous examples, 24% of the M&Ms are blue, but let's pretend we don't know that. So let's forget about this 24%. We take a sample to estimate the proportion of M&Ms that are blue, and suppose you randomly select 50 M&Ms and 16 are blue. Well, you're the statistician. You have a bag full of M&Ms. 50 of them. And it turns out 16 are blue. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 blue M&Ms here. Question says, are the criteria for normality met? What's the meaning of that? It means that, hey, is n times p hat and n times 1 minus p hat both larger than equals to 10? Okay, you should be asking, well, what is p hat here? First, we need to find p hat. P hat or sample proportion is the number of blues, the one that we are finding, 16 divided by how many M&Ms? 50. So this is your p hat. If the p hat is not given to us, we need to find p hat by forming this fraction. 16 blue M&Ms out of a bag of 50 M&Ms. So this is your sample proportion, 16 divided by 50, which is 0.32, or 32% of M&Ms here are blue. This is your p hat. Remember that to form the confidence interval, we need to find p hat. We need that. Now we need to check the normality, n times p hat. N is 50, p hat is 16 divided by 50. We can cancel out 50 and 50. You get 60, which is larger than equals to 10. Now n times 1 minus p hat, which is 50, times 1 minus 16 divided by 50, which is again larger than equals to 10. So the normality is met. The normality is met. It means that this distribution is going to be normal, and we're happy about that. We can move on to find the rest of the information here and construct the confidence interval. Okay, let's move on to next question. Next question says, well, okay, now that you found your p hat, normality is also met, then what is the exact value of your p hat? The exact value of p hat, okay, I know it is, I calculated that. It is 16 divided by 50, or 32%. So just write it again here, 32%. You might feel comfortable writing it as a fraction. Both of them are absolutely fine. Now part C says, hey, now compute the estimated standard error. Standard error, I know I have a formula for that. My standard error, let's get back here. We need to know all of these formulas. Square root of p hat, 1 minus p hat divided by n. So square root of, let me just make this disappear. Sigma sub p hat is square root of p hat 1 minus p hat divided by n, or square root of, okay, my p hat is 32%, 1 minus 32% divided by n, which is 50. When we do the calculation using our calculator, it gives us approximately 0.066. This is our standard error. Okay, now that we have the standard error, we know the next thing that we want is the margin of error. So let's keep this page and move on to the next page. Here we go. We have our estimated standard error. Now we need to find the margin of error. Margin of error is equal to, since it is 95% confidence interval, it's going to be 1.96 times the standard error. We calculated the standard error, 0.066. So it's going to be 1.96 times 0.066, which is approximately equals to 0.13. So again, confidence interval for proportion. Let's summarize what we did here. We found p hat. We checked the normality, and p hat is greater than equals to 10. N times 1 minus p hat is larger than equals to 10. Then we found our standard error, which is square root of p hat, 1 minus p hat divided by n. And then now we found the margin of error E, which is 1.96 times sigma sum p hat. Our next step is to form the confidence interval, p hat minus E, p hat plus E. So these are the steps that we're taking to find the confidence interval. So our confidence interval is equal to, parenthesis, p hat minus E. What is our p hat? We know p hat is 0.32 minus the margin of error, 0.13, comma, p hat, which is 0.32, plus the margin of error, 0.13. This is equal to 19%, comma, 45%. But what's the meaning of that? It means that we are 95% confident that the population proportion is in between 19% and 45%. 19% and 45%. That's the meaning of confidence interval. We don't have the exact value, but we are 95% confident about that. I know this is not exact number, but I am 95% confident that the population proportion of blue M&Ms is in population between 19% to 45%. Very well. So as we saw, p hat minus E, which we call lower bound, lower limit, is 19%, and p hat plus E, which we call upper limit. In this case, in our calculation, it's 45% is on the right-hand side. So in the image below, the sampling distribution is centered at population proportion 24% and an interval that extends the distance of E, where the margin of error to each side is shaded, P minus E and P plus E. So plot the sample proportion as a point, labeling it P hat on each of the number lies below. Okay, here we go. Remember that the proportion, sample proportion for us is 32%, and the population proportion is 24%. So as you can see, your sample proportion is larger than your population proportion. So when you think about it as sample proportion, it's almost here, 32%. And then the confidence interval that we have is going to be 19% to 45%. So 45%, which is here, and here we have 32, which is here. So the confidence interval that we built using a sample, just one sample, is here on the right-hand side. But in reality, for the population, the proportion for population was 24%. So we're comparing a population and a sample. As you can see, one sample is not enough. This is the meaning of these two graphs. In reality, the population proportion is 24%, and the confidence interval P minus E, P plus E, covers the numbers between these two. But if you just take one sample, the proportion of one sample is 32%, and the confidence interval that we calculated is 19 to 45. So let us expand that here, 19 to 45, so it's 32, which doesn't accurately reflect the information that we have for population. So what's the meaning of that? It means that one sample is not enough for us. One sample is not enough. So what's the meaning of that? It means that when you are just finding the proportion for your sample as a statistician, you need to collect as many samples as you can. So we need more samples. If you have more samples, it definitely captures the true population proportion. Very well. Centering the interval at the sample proportion. We have seen that 95% of sample proportions are within 1.96 standard errors, the margin of error of the population proportion. Therefore, for 95% of sample proportions, or p hat, the distance to the population proportion p is less than the margin of error. That means that if we center the interval at a sample proportion, it will contain the population proportion 95% of the time. So that's why we call it a 95% confidence interval. You need to know the 95% confidence interval for a population proportion is p hat minus e, comma, p hat plus e. E as the margin of error is 1.96, times the standard error, which is square root of p hat, 1 minus p hat divided by n. And we need to make sure the normality is met as well. N times p hat is larger than equals to 10, and n times 1 minus p hat is also larger than equals to 10. When the criteria for approximate normality are met, about 95% of such intervals will contain the population, proportion, or p. Again, note that since we are using 95% confidence interval, we're using 1.96 as a fixed number. Well, in our next step, we have one example. This example says, hey, tabulated below are amounts of blue M&Ms from 40 random samples of M&Ms, each of size 50. So suppose we have 40 students in our class and we give each a bag of 50 M&Ms and they count the number of blue M&Ms in each bag. The first student has 8, the second student has 14, the third student has 19, and the last student has 10 blue M&M in a bag of 50 M&Ms. Okay. What is our goal? Our goal is to form the confidence interval. So these are the information that we have, and we are interested in finding the confidence interval. So these are our information. We are about to compute up to 40 confidence intervals for the population proportions of M&Ms. Okay. We calculated one of these intervals in the last question. We saw that. Remember that p hat was 32%. Graph this interval on the number line. You can say, hey, that one was student 27 with 16 blue M&Ms. You can calculate 17, you can calculate 13, you can calculate the rest of proportions for each of these students and find p hat for each of them and follow what we did in previous page for p hat equals to 32%. This was 16 over 50 in previous page. Okay, the p hat that we calculated in previous page had confidence interval, which was, okay, about 19% to 45%. So 19% to 45% roughly here to, where is 45? Just here. So the confidence interval for number 27, which has 16 blue M&Ms, is this interval here. Again, you can calculate the proportion for each of these, follow each of the steps, and find the rest of these confidence intervals. So now the question is, the population proportion of M&Ms that are blue, we know it's actually 24%. In the factory, they calculated each of the proportions They came up with this number, 24%. Plot this as a point on the number line, 24%. Okay, there's 24%. 24% is just going to be a number near here. So this is the actual population proportion, 24%. This is the population proportion. Is this inside the confidence interval? Yes, it is inside the confidence interval, even though it's not exactly at the center, but it belongs to the confidence interval. So the answer is yes. As I mentioned, we can form more confidence intervals based on the information that we have here, and we can repeat the process finding the rest of these confidence intervals.